So I've been looking at this and thinking about how you might implement the idea of a discrete space-time. Now, the first thing to say is there are any number of ways to do it. And if anybody says there's some physical consequence of just having a discrete space-time, that can't be right because there are just too many ways to do it. You can't just saying it's going to be discrete doesn't tell you enough. I've been thinking about how to do this in a novel way that I call full discrete geometry. So I'm going to tell you about that very quickly, and starting with the purely spatial structure. So now forget about time. Time's going to play a very important role in a minute. But for the moment, just forget about time and just think about space. What could a discrete space look like? Well, the thing I'm calling full discrete geometry is called full because it has atomic elements of all dimensionalities up to the dimensionality of the space. So if I have a three-dimensional space, I'm going to have zero-dimensional atomic elements, one-dimensional atomic elements, two-dimensional, and three-dimensional atomic elements, which, for obvious reasons, I'll call 0, 1, 2, and 3 elements. By saying they're atomic, I mean they don't have any parts of that kind. So the zero elements are zero-dimensional atomic things, zero-dimensional things that have no parts. So you can think of those as points. That's fine. That's what we always thought points were. One elements will be one-dimensional atomic things, atomic lines, if you will, but you can't think of them the way you do in Euclidean geometry. In Euclidean geometry, lines are made of points. In fact, every line, no matter how short, is made of an infinite number of points, because in Euclidean geometry, you can always bisect any line and then bisect that and then bisect that and then bisect that forever. So these atomic one-dimensional elements are not composed of points. They don't contain points. They are bounded by points. Each one is bounded by a pair of points. So the fundamental relation between different dimensionalities of these elements is that some bound others, right? N elements bound n plus 1 elements, if there are any. So every one element has exactly 2 zero elements as boundaries. And once you specify what bounds what, you can then make decisions about what is adjacent to what. So in a discrete space, unlike in a continuum, if I pick out a point, I can ask what are the nearest points to it, the ones next over, the adjacent ones. In a continuum, there's never an adjacent point. There's always, no matter how close I come, there's closer ones. And in a discrete space, there are adjacent ones. But once I have this relation between the zero elements and the one elements, I can say what is adjacent to what. So if I have a zero element and a one element and another zero element that is its other boundary at the other end, then I would say those 2 points are adjacent. And if I have 2 one-dimensional lines and they share a boundary, if they are both bounded by the same point, then I'll say they're adjacent. Good. So all of that is going to be well defined. So here are some examples of one-dimensional discrete spaces. They're made up of zero elements points and one elements these lines. The middle one is what would normally come to mind if I said, give me an infinite one-dimensional discrete space. Okay, it's dot line, dot line, dot line forever. But from what I've said, the other ones are perfectly good one-dimensional discrete spaces as well. In the upper image, you'll notice there's a point that bounds not 2, but 3 different lines. In the lower image, you'll notice that there's a loop, but you should not think that that loop itself is the boundary of a pentagon or anything, because there are no two-dimensional elements at all. They're only one-dimensional and zero-dimensional elements. So these are some discrete spaces, discrete one-dimensional spaces. They're not all that interesting. Things get interesting when we go up to 2 dimensions. When we go up to 2 dimensions, we now have to make a decision. Namely, what do our 2 elements look like? What do our atomic surfaces look like? What kind of geometry do they have? And here you have a choice point. And you have any number of choices you could make. And so, as I said, again, if someone asks, what are the physical consequences of making space and time discrete? The answer is, you have to tell me a lot more before I can answer that. Now, physicists have looked at this. The most common, and as far as I know, almost the only choice that's ever made is what's called to use a simplex as your two-dimensional element. And a simplex, as the name suggests, is the simplest two-dimensional polygon, namely the triangle. And then if you go up to 3 dimensions, the simplex is the simplest polyhedron, namely the tetrahedron, which is, of course, made of triangle. I mean, its bounding faces are all triangles. And so lots of physicists who have looked at the idea of a discrete, somehow discretizing space or discretizing space and time, immediately go and do it in terms of what are called simplicial complexes, sets of these simplexes, which means you're dealing with points, lines, triangles, tetrahedra, and so on. That's not what I'm going to do. So this is the first thing to notice. And it's not obvious what to do. And when I was writing the chapter on this, I rewrote it 4 different times, first with triangles, then with square, as we'll see, with quadrilaterals, and then back to triangles, then back to quadrilaterals, back and forth, until I figured out what actually made sense. In any case, what I ended up doing, and the thing that works for my purposes, is when I go up to 2 dimensions, not to use triangles, but to follow Euclid. So what did Euclid say? Euclid said, a point is a dimensionless thing, right? It has no dimensions. If I take a point and move it, again, now through a continuum, it draws a line. So that gives me a 1-dimensional thing. And now if I take the line and move it, the whole of it, in another direction, if I have another direction to move in, that will trace out a quadrilateral or a square. I mean, you might say a square, right? I take my line and now I move it, and now I take that square, if I have a 3rd dimension and I move it, it traces out a cube, or properly a heptahedron. So this is what we're going to do. We're gonna take as our 2-dimensional elements, not triangles, but quadrilaterals. I'll call them squares because it's easier, but they're not officially squares because I haven't defined angles or lengths or anything that you'd need to really define a square. And the 3-dimensional elements will be, we'll call them cubes. Again, they're just things like cubes and square-based solids of that sort that have 6 quadrilaterals as sides. Okay, so sorry, again, this is where I'm just saying you right, 1 dimension, 0 dimensions, 1 dimension, 2 dimensions, and then pull that up 3 dimensions. Good. So let's just look at the 2-dimensional case, pure geometry, pure spatial geometry. And so this picture, the square grid, is the space. The elements of the space are a finite number of points, which you can think of as the vertices here, or where the lines intersect. A finite number of 1-dimensional elements, which are easy to see, and a finite number of 2-dimensional elements. And the 1-dimensional elements bound the 2-dimensional elements, the 0-dimensional elements bound the 1-dimensional elements, and so on. Now, that space has a kind of intrinsic geometry to it. Even though I haven't defined length, even though I haven't defined angle, there's a natural way to talk about the geometry, because when you do discrete things, there's always what's available counting measure. You can always count things to get a kind of sense of, as it were, how big they are. And the geometry you get in this case is what's called taxicab geometry. It's kind of familiar because it's what would happen if you got into a cab in a city with a square grid of streets and you tried to figure out how much you're going to have to pay to get from point A to point B. It doesn't really matter, as it were, how far point A is from point B, but it's how far the cab is going to have to drive, and it's got to be constrained to stay on the streets. So in this picture, you'll see point C, and then these other points that are indicated with the dashed lines between them, they would be what would correspond to a circle in this geometry. That is, those are the points that are 3 units away. That is, the least number of moves you have to make on this grid to get from C to any of those points is 3. So you can go, 3 out straight to the right, 3 out, 3 up, or you can go 2 up and 1 over, or 1 over and 2 up, and you get this thing that is what corresponds to a circle. And of course, it's not a circle. It doesn't look like a circle. And it not only doesn't look like a circle, these things don't behave like circles. They don't behave in a very fundamental way like circles. So if I look at point D in that diagram, and again, start growing circles out from it, which will be these growing diamonds, you'll notice that when they meet, when the circle of 3 units from D will meet the circle of 3 units from C along that entire edge, along an edge that contains 4 different points. And that can't happen in Euclidean geometry. In Euclidean geometry, if I have 2 circles, they either don't intersect at all, or they intersect at 1 point, or they intersect at 2 points, and that's it. They can't intersect at 3 points because 3 points determine a circle. So even without talking about lengths and distances, just topologically, these things that correspond to circles in this taxicab geometry don't behave like circles. So this is very non-Euclidean. It's of course also very non-Euclidean because you don't have an infinite number of directions from any given point. You only have 4 directions you can go in from any given point. Good, so that's the discrete spatial geometry. Now we're going to add time. And we're going to add it in a discrete way. So again, just as for any spatial point, you can talk about the next ones or the nearby adjacent ones. Now, for any event, you can talk about the next ones or the most adjacent ones in time, the ones that happen next from that one. And so because time, unlike space, has a direction from earlier to later, we're going to use directed elements, arrows, rather than undirected elements. So we're doing directed graph theory now, as it were. How am I going to add the time structure in? Well, again, I have an infinite number of choices. Even in the simplest case, which is 1 plus 1-dimensional space-time, so 1 dimension of space and 1 dimension of time, as always, there are infinitely many ways to do this. Let's just look at some of them.